Here we have our last example in using gamma functions to solve different types of integral problems. And here we want to consider this integral here where we have 3 to the minus 4z squared dz. Z goes from 0 to infinity. And looking at this, it seems like it's a far cry from a typical gamma function type integral. And the trick here really is to remember how exponentials and natural logarithms function. Remember now that e to the natural log of x, by definition of course, that just equals x. So I can use this to rewrite this integral here. That's no big trick really. We have this, and then we would have e to the natural log of that, to the natural log of this expression. 3 raised to the minus 4z squared. dz. E to the ln of this is just going to be that. That's just simply as basic definitions of the natural log. Now, if we have it in this form, and say, well, we still have a problem because here we have e to the minus x, or e to the minus variable, and here we have e to the natural log of something here. But let's see, what happens if we try a substitution? What if we say, well, first of all, we can take one more step of this here. We can rewrite that, again, using the properties of logarithms. See if this helps us out. E to the natural log of 3, and then we would have here minus 4z squared times that. That again is just using basic property of logarithms. And here then, if we say, well, we have a dz of course. Let's try a substitution. If I say let u be equal to this, we would have u is equal to minus 4 times the natural log of 3 times z squared. No, we want the minus sign in there, so we'll just say let u be equal to 4 times the natural log 3 times z squared. If you make that substitution, that gives us e to the minus u. That's resembling a gamma function. But what about the rest of the integral? Well, if we go ahead and work with our substitution, as in the previous examples that we worked with, maybe the other parts of the integral will kind of fall into place then. So let's see, if we have this du, that will equal 8 times the natural log of 3 times z dz. Now, once we start doing this, then, we want to have dz expressed entirely in terms of the variable u. But let's start with this. We'll say, well, dz, that will equal 1 over 8 times the natural log of 3, dividing both sides by this, z to the minus 1 times du, and now we have to get an expression for z in terms of u. So we go back here at our basic definition, and we have, well, z squared, that will equal u divided by 4 times the natural log of 3 So z, if we take the square root of both sides, that will equal plus or minus, this would be u to the 1/2 divided by 2 times the square root of the natural log of 3, and we're just going to consider the plus part here. So this is z, z to the -1. We raise this whole thing to the -1 power. That'll bring this upstairs. So that will be 2 times the natural log of 3 times u to the -1/2. So let's go over here then. We're going to have dz will equal this times z to the -1, that's this. And this actually should be 2 times the square root of the natural log of 3. Okay, so then we're going to have 2 times the square root of the natural log of 3 times u to the -1/2 du. Here we had dz is 1 over 8 times the natural log of 3 times z to the -1, and z to the -1 is this. So we have 2 times the square root of the natural log of 3, u to the -1/2 du. So it looks like we have all the pieces of the puzzle that we need. This is going to be e to the -u by our substitution, and now we have an expression for dz that is expressed in terms entirely of u and du. So let's see, if we go back, our original integral was this. 3 to the -4 z squared dz, and we rewrote that as the integral 0 to infinity of e to the -4 z squared natural log of 3, and then we made some substitutions. Notice now, z goes from 0 to infinity. If z is 0, u is 0. If z is infinity, u is infinity. So this integral here now is going to become, this will be on the outside, so we're going to have 1 over 4 times the natural log of 3. And then we'll have the integral, u goes from 0 to infinity, and we're going to have e to the -u, that was just from our substitution here, and dz is u to the -1/2 du, and this we already took care of out here. So this integral is transformed into this integral, and we see, fortunately, we caught a break. This is a gamma type integral, and in fact we look at that and hopefully you realize, yes, that is the gamma function of 1/2, and that's equal to the square root of pi. So this integral here will equal this times the square root of pi, so it looks like it's going to be 1 over 4 times the square root of pi divided by the natural log of 3. And that's the solution to that integral there. So again, when we started out, it looked like this was going to be a far cry from a gamma-type integral, but we had to remember the properties now of logarithms and rewrite it like this, which put it into this form, which allowed this substitution here, which ultimately got it down into this integral here, which in fact did turn out to be a gamma-type function. Okay, that's it. What we're going to do in the next video is consider beta-type integrals.